Lerman from the University of Minnesota does really nice things on constraints and things like that. And he's going to tell us about problems of robust high-dimensional statistics.
Thank you. Thanks a lot to the organizer, especially Elias. It's really great pleasure to be here. It's actually my first time here. I was actually very ambitious before I'm planning to tell you about. I'm not going to tell you about many problems of robust high-dimensional statistics, but mainly on one problem. And the issue will be on robustness, not so much on the high dimension. Also, let me mention it's a joint work with Tyler Mono. I'll actually mention all the credit at the end, but it's important to say that all the new results here are joint with Tyler, and Tyler actually led the work, so it's sort of a showcase for Tyler. He's now at MIT. Before telling you where I'm going to, probably I should tell you where I'm coming from. And this is actually relevant to a lot of other talks, but even though I don't have much time, I think it's important to mention it. So robustness has a very long history. So it actually goes back to Adam and Eve. I'm not going to tell you about the times of Adam and Eve, but I'll tell you about the times of people who challenged the theory of Adam and Eve, and we'll go back to Galileo. So if you go back and look at science, and even science today, most scientists know two kinds of things about robustness. So if they are kind of advanced mathematically, they know that you don't need to use least squares, but you need to use least absolute deviations. And I think the audience here is well familiar about least absolute deviation line versus least squares line. But maybe you don't know the long history. And as I said, it already goes back to Galileo Galilei. The other example is very simple idea of rejection of outliers. Okay, so even if you don't, scientists who don't know much about mathematics, they know they have to reject outliers. And in terms of quantitative history, I could list the following people. And it's interesting to see actually that it is sort of American topic. So there are two Americans from the 19th century, and when Anscombe wrote a paper about it, actually he mentions that it's an American topic. Being here actually at Berkeley, at the campus of Berkeley, it's maybe the best place to talk about Great America. But I have to say a comment, looking at the diversity of the speaker here and the next slide, this is not the kind of America or kind of world I would like to make great again. So, okay, so this is about history of robustness, very early history. Then comes the theory of robustness, which started in 1960, and actually in the morning talk there's already some review about it. And when people think about theory of robustness, people think about Huber, who defined robustness very well in terms of insensitivity to small deviation from the assumptions, which made a lot of sense when he started working on robustness, and most models were of Gaussian distributions. And he actually talks about two works which were influential to him. So one of them actually we heard about this morning, the work of Tukey, which started some mathematical analysis that later resulted in the minimax analysis of Huber, which you also heard about this morning. The other influential work is by Anscombe about rejection of outliers, where he talks about the idea of paying in front for insurance policy if you want to deal with outliers. And he has a very natural trade-off with performance. What is interesting, if you read one of the assumptions, he talks about having to ignore computational cost, and this was in 1960. It's interesting to see that all of these people had very strong effect on computation nowadays, but in the 1960s they didn't, and when they had to analyze robustness, they didn't care about computation. According to Huber, actually the credit for the effect of computation on robustness goes to Bickel. So why do I actually do this kind of introduction? Because I really think, these kind of ideas actually are rooted with very basic ideas coming from science, which I reviewed before. And this is about foundation of data science. So we have to really care about the basic ideas that the data scientists care about before we develop theory for it. There are also very nice ideas of presentation, both in writing and both in talks, that we should probably follow. There's a nice emphasis on computation, but computation cannot be any polynomial time algorithm. It has to be reasonable computation. And there are many other aspects coming from statistics. It's not just robust to outliers. You know, if you have some assumption on your model, you have to be very flexible when you change your model, the model of the inliers. You have to consider other aspects, for example, causality, which was actually discussed this morning. So keeping all these things in mind, I would like to move on and talk about one problem that I know quite well about, which is robust subspace recovery, and I think it's very natural, so I want to review it and give you some insight. And then I talk about new result for the adversarial case, and I think most people here actually care about the adversarial case of outliers. And I was actually ambitious and thought I can also talk about related problem, but it probably has to be avoided. Okay, so what is the robust subspace recovery problem? So mathematically, it's very simple. So we can think of this cartoon, and we have inliers coming from a given subspace. They can either be exactly on the subspace or around this subspace. So my inliers are the x's here, and outliers, which are represented here by red circles, and they come from a different distributions, possibly away from this subspace. So someone is giving you this data and asks you to find the hidden subspace. Okay, so this is what we call robust subspace recovery. Any questions about it? Okay, so it seems simple. So why should we care about this problem? So this is the foundation of data science. So what do data scientists care about? They care about PCA. Okay, and PCA in terms of subspaces, we all know that it's actually, it gives us a subspace that minimizes the following least squares energy. Okay, and we all know why PCA is great. It's a very basic generic tool. If I give you a data in high dimensions, so noise is amplified in high dimensions, I reduce the dimension with PCA. It has very nice properties. And then it's able to somewhat denoise the data, so I can I can successfully do different tasks in the low dimension. For example, cluster this data. Okay, so it's a very useful generic tool. The problem with PCA is that it's not robust to outliers. So in this cartoon, we have points on this line, and the PCA lines find another. It's different than the hidden line here. So the goal of robust subspace recovery is kind of to develop alternative to PCA, which is robust to outliers, but also has the nice properties of PCA, for example, the attractive computational power. So actually, there are three main approaches to robust subspace recovery. And these are these approaches are so basic that we have seen them in previous talks. So one approach is just to search exhaustively for this subspace. And people had this similar approach in previous talk. They call it brute force search. The other approach is to reject outliers or filter outliers. So we had very interesting filtering algorithms in previous talks. And then there's the idea of energy minimization. And there are different kinds of energy. So one simple energy is the least absolute deviation energy. So before I told you that PCA has the square here, and now we drop the square and we try to minimize this least absolute deviation, but there are many other important methods. So, everything seems very simple, and no one asked me questions so far, but actually I tricked you a little bit. So this formulation of RSR is not well defined in general. What do I mean? So I can create a data of inliers and outliers, where inliers are on a line and outliers are away from the line, but there is no really underlying subspace in the data, or we cannot agree that there is a unique one. For example, the most trivial case, if all my inliers are at the origin and no outliers, then any line here will be okay. So the problem is not well defined. Of course, I can generalize this case and have inliers actually concentrated on a low dimensional subspace. And now if the outliers also happen to be in another subspace, it's possible that someone will output another subspace, not the one actually originally meant to have. So we need to have some general principle which you can actually express mathematically in different ways, and also see it in other ways of works actually reviewed in previous talks, or mainly yesterday. that inliers must permeate L star, so we cannot concentrate on low-dimensional subspaces of the underlying subspace. We also need to restrict the outliers, so the most extreme example is when the outliers are on a line. Okay, and then in this case, we can associate this line. In this case, when we have underlying line, we can think this is the main line, or we can take part of the outliers here and part of the inliers and have another subspace. So it actually gives rise to another principle of restriction of alignment of outliers. There are other examples. I won't get into them. There are many examples. It's a more complicated notion. But in this particular example that I talked before, you see that there is some interplay between the two principles. So I want to have the inliers permeate throughout the whole subspace, but I also don't want the outliers to concentrate on a lower dimensional subspace. So one more clarification is that for simplicity, I assume that L star is a linear subspace. Otherwise, I have another parameter and the problem becomes more complicated. I also want to clarify that it's kind of inherently non-convex formulation. So whatever method you have to recall that after all, you're looking for a subspace which belongs to a set of all d-dimensional subspaces in Rd, that is the Grossmanian. And this Grossmanian is a non-convex set. So you're searching in a non-convex set. So whatever you're going to do is going to be inherently non-convex, even if you convexify it. Important problem for practitioners, this scale is very important. So I can give you this cartoon and I have two subspaces. I have this line and that line. And I can compute the error with respect to this line and error with respect to that line and see that I have a very large error with respect to that line. So maybe this is the line that describes the data. But if I also take into account the scale with respect to the origin, I see that this might be an outlier and we need to reject it. Okay, so it's something we need to keep in mind. And there are methods which are scale invariant in the sense that do not weigh the magnitude of a data point. Actually, we all know, maybe you don't recall right now, that any method can be scale invariant. How do you make any method scale invariant? So you just, you have your data, you scale it to the sphere, right? You divide each point here by the norm of a point. Okay, so now with respect to the origin, the points are on a circle. And now, okay, so now we scale the data to the sphere, and now we apply the method. I say we all know it because practitioners in data science know that before they apply PCA, they better scale the data to the sphere. So it's called spherical PCA. Okay, so this is very, very common. And it's just a comment that as long as, in our setting of linear subspaces, we can scale the data to the sphere and have scale invariant methods. Small comment is that, there are instances where scaling data to the sphere actually makes the problem worse. Here you have lines of inliers and few outliers at the origin, but when you scale things to the sphere, outliers actually become worse. But this is one pathologic example. Okay, so now this is the foundation workshop, and the question is what kind of theoretical setting exists for robust subspace recovery? So one setting that people here care about is adversarial outliers. But as I told you, yeah, Boaz.
The question, don't you want it to be invariant to shifts, where you decide where your origin is?
Okay, so I had my original assumption that the subspace is linear. So I take into account the center. I remove the assumption of centering the data. But there is...
The outliers,
No, so currently for our theoretical analysis, okay? You can then talk about the case of affine subspaces, and you have an extra parameter. You also need to evaluate it, and you also know some methods about symmetrization that actually sometimes are relevant here also. Okay, so any other questions before I move on? Yeah.
You kind of ignore the issue of prior knowledge. I mean, when I talk about model and outliers, it's kind of meaningless if I don't introduce some prior knowledge about the problem, because Otherwise, why do I prefer one model over another?
So I'm not sure I'm following you. Let's see, I will give you some models, more specific models, and see if they're satisfying to you or not, okay? Okay, so the case of adversarial outliers, but I already told you that the problem can be ill-defined in general, right? So we need to make sure that the inliers are permeated in some sense. We also need to, we don't restrict anything about the way outliers looks like, but we need to restrict the fraction of outliers, otherwise we cannot solve the problem. So we need some bound on a fraction of outliers, an upper bound, or a lower bound on a fraction of inliers. I usually like to have a lower bound on the fraction of inliers per outliers, which I called SNR. So I think of the inliers as a hidden signal, or the subspace as a hidden signal, and the outliers as noise. Okay, so setting of anything that you have on outliers, but you have restriction, a lower bound of the SNR, and you have permeated inliers in some sense. One important comment, you have to formulate it for scale invariant algorithms, because otherwise the other algorithms have some restriction on the magnitude and they cannot deal with any outlier. Okay, so this is one example. Now, people also talk about statistical models. The reason why they want statistical models, because in practice, here you have to restrict the fraction of outliers. But there are data sets that have a lot of corruptions. They have many, many outliers, but they have some more assumptions on the way the outliers are generated. So that's why you have to deal with different statistical models that allow you high corruption or low SNR. Now, another strange model, actually, very artificial model, but actually it turns out to be very, very interesting in theory, is of inliers and outliers in general position. And I'm taking the definition from a paper by Hart and Moitra, where they say that, actually maybe let me make sure you're all with me. So when I say capital D is the ambient dimension, and little d is the intrinsic dimension of a subspace. Okay, so any set of capital D points are linearly independent unless it includes at least d plus 1 points from L star. So in some sense, L star is the only subspace in your data. Like everything else is very independent with respect to it. The outliers are very independent, not just of course, if I take only outliers, they're independent, but also if I take only few inliers, they will be independent. So why is it important? So we have a very interesting result that says that for not just for this case, in general, if your SNR, fraction of inliers per outliers, is less than the intrinsic dimension over the differences of a dimension, or the dimension of the orthogonal complement of a subspace, then the problem is small set expansion hard. And then they want to see that they actually can still get above this SNR, so they use this particular model and show that they can actually exactly recover the subspace with certain algorithms. They show, and also other people that follow the work show, Teng Zhang and Eli Arias-Castro and Wang. So it is very interesting in terms of the theoretical aspect of the hardness threshold, but it's not a real model for applications. So I would rather concentrate on these two models. Yeah.
Is it always information theoretically possible? So is the problem always identifiable? Are there any information theoretic limits?
In terms of what? Because
in terms of the SNR.
So they tell you, that if you assume, in general, SNR cannot be less than this. But I can have specific models where I can have lower SNR. Right? If I have Gaussian inliers and Gaussian outliers, I can take the SNRs to goes to 0, because it's really easy to see the line or the subspace.
So in this particular model, the model is always identifiable.
So what you're asking me about the GP model, right? So I know for sure, so I know they have this, but I don't know if in this particular model you can go down. I'm not sure. I know that they did it for the general case. I have to go back to the paper, and I can't answer you this
If you're GP, can't you just take little d plus 1 points and until you find them that are linearly dependent, and then say the subspace they span is the Planted subspace?
Yeah.
Yeah, but that's not polynomial time.
Yeah.
If it's information,
It's an information
if it's
theory.
identical.
No, oh, okay. So you're talking about the information theory. Yeah, okay, sorry. So I didn't understand the question. You asked about just the information theory, not about the computability. Yeah, so this is true. So it's enough to, once you have d+1 points, information theoretically, it's enough. Okay, I misunderstood your question. Very good. Thanks for clarifying. Okay. And actually, we'll get back to it. Okay, so what methods have been done for adversarial outliers? So at least in the subspace recovery, the most kind of likable method is outlier pursuit, which has pretty big SNR. So you have a big constant times little d, the intrinsic dimension, times an incoherence parameter. So I would actually, I'm not going to define it here because it's not a natural parameter for this setting. It's very natural for compressed sensing. It's natural for the low rank plus sparse setting. But I don't think in this geometric setting it's a natural parameter, but it can be pretty large too. I just tell you that it's kind of inversely proportional to the permeance of the data. So it's kind of a way to measure the inverse permeance of the data. There is even a slightly bigger constant with another algorithm. And then there have been some exciting ideas, but not for this problem, but I still mention them here. One of them, for example, is for detecting Gaussian, which you can also talk about Gaussian on a subspace, but it's actually for a very different setting. So now let's ask several questions regarding this setting, and one of them is the question that you just asked me. So what are the questions? One is, what is the lowest SNR with well-defined setting, or as you can call it, the information setting? The other thing is there any hardness result for lowest SNR, which we already kind of talked about, but in how it plays in this setting, and what is the lowest SNR obtained by a reasonable time algorithm for exact subspace recovery, and all of this is kind of very theoretical setting, but I want to see an algorithm that is actually very competitive, that it works not just for very clean setting, but also when I have a little bit of noise and when I have, and it has some flexibility to other models. Okay, so recall our initial setting, and as I said before, the problem is generally ill-defined. So the question is first to understand the the information limit. So what is the smallest, in the case of adversarial outliers, what is the smallest SNR? So Shukar, Armanis, and Manor claimed it's order of D, and they gave an example where actually on each line of a subspace you have some inliers, but it's a problematic example because the inliers are not permeated throughout the whole subspace. Okay, so the reason why they got the order of D is not because of the information limit. And indeed, if you assume a case of permeated inliers, for example, you assume a different notion of general position, only for the inliers, that any D points in L star span L star, okay, then you can see that for the adversarial case, you have a well-defined setting if the number of inliers is almost bigger than half of the points. Okay, so you have about 50%, more than about 50% inliers, or SNR of order 1, at least order 1. So this is for the case of general position inliers, but anything about the outliers. If you also have general position outliers, but I slightly defined it differently than before, I can show you that the problem, and actually already gave us a proof, the problem is well defined with the number of inliers is bigger than little d. And now you can have very, very small SNR when n goes to infinity. Okay, so now the question is computationally, what are the limits? So we already mentioned to you a result that tells you that you cannot have any small SNR. So Hart and Moitra tells us that this is the bound of an SNR. So we know that it's too small. The too small SNR that we talked about before. has a limit. We can't go with any small SNR. But actually, the result is also relevant for the adversary case, where I told you I have order of 1 SNR in theory, because what happens here, if you have very high dimension of little d, so d minus d is 1 or order of 1, so if you compute the threshold that they give, little d over 1 or order of 1, you get order of d or order of capital D. Okay, so you can't go below it. And this is why I think you see in Karamanis the order of d factor, not because of the example that they give you. So now the question is whether we can actually obtain this fraction by an algorithm. We saw the algorithm of Shu, Karamanis, and Manor, where you get such constant time little d, but maybe you can get smaller constants. So before I move on, any questions about it? Okay, so I'm going to give you an algorithm that will prove the point that actually you can get a constant like this. It's not a practical algorithm, so I don't want to spend too much time. And if you need to, if you have short attention and you need a break for a minute, so you don't need to follow, but then get back with more concentration. So what is the best SNR for that one can get, or one of the so best SNR that we can get is with a brute force search, which is called by electrical engineer RANSAC type algorithm. So the idea is very simple. We take random subset of X that spans a D subspace, okay? And now we check, we take the span of these points. So now we get a subspace, the span of these points. Now we take the number of points that have angle with L less than a certain consensus parameter. So you can even take, in the clean case, tau to be 0 and just count the number on the subspace. Okay, and once you're bigger than, you have more points than a certain parameter, little m, which will be half of the number of points, you're fine, and you output L star. But it's possible that the number of iteration, already passed and you didn't find this subspace, so you just output the subspace with the largest number of points. So it's a very simple RANSAC algorithm. So what we can show for this is, first of all, if the SNR is bigger than 1, and you run it sufficiently for many number of iterations, and you have sufficiently small parameter tau, and your parameter m, the consensus parameter of counting the number of points on the subspace, is bigger than half of the points, you can just take it to be half of the points, then L star is recovered with high probability, but you can have exponential time. But if you restrict the SNR to be bigger or equal than C times little d, so L star is recovered with high probability, and it's enough to take the number of iterations to be order of 1. So the complexity is order of the number of points times the ambient dimension times the intrinsic dimension. So the main issue now is to come up with a more really robust algorithm, in the sense that if we, it's robust to other setting, not just to this very artificial setting of adversarial outliers. But before I move there, I just kind of mention one small issue, which actually I cannot resolve. So what we noticed is that, especially when we enlarge D, we can take C to be less than 1. And if you notice, actually the threshold by Hart and Moit actually said that C has to be 1 when little d is equal capital D minus 1. So we can take, when D goes to infinity, we can take C to goes to, C can be any positive number. So something goes wrong in terms of what happens with their hardness of computation threshold. And I'm not sure what's going on wrong, but it's something I'll be happy to discuss with people here. And I had Ari check our argument, which is very simple. So I'm sure we have C, which can be less than 1. Okay, but let me focus on kind of a more interesting algorithm. And I want to, as I said, present something which is more robust to other setting, not just to the very specific setting of adversarial outliers. But it also works well for adversarial outliers. So let me show you what you get and somehow compare it with the common algorithm of Shu, Karamanis, and Manor. So in order to follow what we have, I need to review what I call the well-tempered landscape of this energy function and the geodesic gradient descent algorithm to optimize this energy function. Okay, so what I mean by well-tempered landscape. So, one thing you have to keep in mind is that this gives rise to non-convex optimization. So again, this energy, as a function, it's a nice convex function, but we actually minimize it over the Grassmannian, the set of all surfaces, which is not convex. Okay, so we have a non-convex optimization, which may have many local minima. PCA is also non-convex optimization, but there is something very interesting that happens in terms of local minima are the same as the global minima. So this is not the case here, but under certain conditions, the energy landscape behaves very well. So, okay, thank you. So just to exemplify it, let's take this cartoon of data, which was generated from a certain statistical model. So we have points on the line. We only have 6 points on this line, and we have outliers. And now we want to see how this energy behaves like. So we identify, the surfaces are just lines through the origin, so we identify them with the angles they make with the x-axis. Okay, so this line, the x-axis itself, is either the angle 0 or the angle pi. I just divide the angles by pi, so this is the same. This line is has the angle pi over 2, or 1/2 here, which is the global minimum of this energy. And now we notice that there is a neighborhood around this line where the energy landscape behaves very nicely. So there is a nice, strict decrease of a cost function towards the global minimum. Outside this neighborhood, we can have different local minima. Even in the neighborhood, things are nice. It's possible that, things are not differentiable, but the subdifferential is still negative. So we have a result which says that this works in general. There is a certain stability condition that under which you have this what I call well-tempered landscape. Now you can also show that in this neighborhood, under this condition, geodesic gradient descent algorithm for this energy function will converge sufficiently fast to the subspace L star. And under a similar condition, you can actually initialize by PCA in this neighborhood. Okay, so it's a very simple algorithm. You start with PCA, and then you run geodesic gradient descent, and then you converge to the subspace L star, and it will work if a certain condition is satisfied. So now I want to check this stability condition under the model of adversarial outliers. So now what we have to keep in mind, the geodesic gradient descent is problematic for adversarial outliers because it's not scale invariant, right? If I have, the magnitude of the points affects this energy. But I told you what one should do. So we're going to talk about spherical geodesic gradient descent. I'm going to sphericize my data in the following way, divide each point by the norm. And this is the data matrix, we'll now denote it by x tilde. And then I will apply the GGD algorithm. So in order to analyze the performance of this algorithm, I want to introduce a very natural spherical condition number of inliers. So I take my data matrix of inliers, so the columns, which are the data points, are scaled to the sphere, and actually look, so this is the covariance, the empirical covariance matrix of the inliers, and I take the largest eigenvalue and divide it by the dth eigenvalue, and this is my condition number. So if my inliers are nicely permeated, it's of order 1. This small eigenvalue is like this one. But if they are not nicely permeated, then I have a big gap. Okay, so it's actually inversely proportional to the notion of permeance. And now the miracle is that the stability condition for this algorithm, when I initialize it in a neighborhood of radius gamma, is the following one. So I need to have good initialization. Now, usually I initialize a PCA. What's the result for PCA? So the result for PCA is that if the SNR is bigger than this quantity, then I can, and I apply SPCA, spherical PCA, then it will be in this neighborhood. It won't find exactly the subspace, but it will be in this neighborhood. And now if I combine the two together and choose the right gamma, it doesn't matter to me which gamma, I have it, if my SNR is bigger than this number, then this number times little d times the spherical condition number, then I have well-tempered landscape, and then the SGGD initialized with SPCA will find my subspace. If you want it to be really, really fast and have linear convergence, I have to slightly change my condition and have the following thing, which is not such a big change. And if you want to know something about the spherical condition number, so at least if you have isotropic Gaussian distribution of inliers, this is the order of the spherical condition number, just a constant, and it's not a large constant, unlike what you have in Shukar, Manis, and Manor, which actually can grow like log n. So I have a quick table of comparison. I won't have time to go through it, but we have our SGGD, and you can compare it with the outlier pursuit and torque, which has bigger constant and different kind of notion of inverse permeance parameter, unlike the kappa here. The other works not exactly on this topic, but I just mentioned them here. I don't have time to review them. They are not about exact recovery of subspace. There is a result for the spherical PCA, but it's not about exact recovery, just about approximation. And there is the RANSAC type algorithm, which is not a really practical algorithm in general. So maybe to say something that, the SGGD is practical, it also works well with other statistical models. I don't have time to do it here, but if you check our paper on the geodesic gradient descent, you will see that actually, we have different statistical models, and it even adapts to different regimes of samples. So for example, if you have Gaussian inliers and Gaussian outliers, if the number of outliers is bigger than some in the following threshold, you can actually deal, for given SNR, you can deal with this SNR. So you can actually take the SNR to goes to 0 in this model and still deal with the data. So this is back to your question, but you can, it can happen in some situations that you can deal with very small SNR. And also under this model, you have very nice complexity for SGGD. So it's time to start summarizing. So I'll just mention that, I didn't touch in open directions in RSR. So for example, I didn't talk at all about noise. We have some result for small perturbations to noise, but only few results which shows that nice behavior to noise, but I don't have time to review them here. But I would really like to see analysis for spiked model, which is actually missing. The questions about really large sample and high dimensional limits, especially in terms of computation. What happens if you can't store the data on one machine, you want to work on a distributed machine, or this would network. How do you estimate the surface dimensions? So Edgar, who is, I don't see him right here, has very nice theoretical result about estimation of surface dimension for PCA, but I don't see how it applies to robustness recovery, and it will be really interesting. First, clarification of trade-offs will be interesting. Case for application. So I told you it's a version of PCA, but I want to see more evidence that it indeed improves over PCA. So I have few examples where I know it can improve, but in a lot of cases that I saw, the improvement is not high enough. Or at least not as high as spherical PCA, which is the choice of many practical people. So I would like to see a very careful study of this. The other thing which kind of disturbs me, we kind of advocate for gradient descent, and there are so many methods nowadays of gradient descent, and it's becoming maybe intellectually boring. So I know we have other methods that work even better in practice, but we don't have nice theory for them, and it will be interesting to see how maybe theory for other methods which are not gradient descent. And there are other specific issues. There are many other problems that the analysis I talked about here is very relevant to, but I don't have time to talk about it here. I can discuss it with you later. And let me just give you a few take-home messages. So robust subspace recovery is a very basic problem. I think it's motivated from data science, and it raises interesting questions. I touched a few of them, but there are many open questions. And I gave you here a clean treatment of the case of the adversary or adversarial outliers. The LAD RSR optimization is non-convex, but still we have a non-convex algorithm with guarantee that is shown to be fast and flexible. And the ideas that we have developed here seems to extend to the other problems I mentioned before. I had in the slides before, but didn't have time to talk about. And actually, I collaborated with a lot of people on robust subspace recovery or low rank approximation, and learned from a lot of collaborators. But mainly in this talk, I highlighted the collaboration with Tyler Monu. And as I said before, it's really, the new results, it's really showcase for Tyler, who is now at MIT. Thanks.
You say you had adversarial outliers. What is the adversary allowed to do when he produces outliers? Can you put them anywhere, or?
Yeah, you can put them anywhere, any size, any magnitude. Yeah.
And he can try to put them all in a different subspace to fool you?
The worst case is when the outliers are on a line, in some sense. Yeah.
Good question. So you talked about convergence of a Riemannian type gradient method, and that seems like it's assuming you know the correct dimension of the subspace.
Sure.
That's true?
But okay, so actually this is true. For okay.
That's my first question. I'll have a follow up shortly.
So okay, you get so you have a general theorem that you have, if under a certain condition something happens, then you have this so if you have under certain condition very nice things happen. But in real situation, you really need to know the dimension of a subspace, so the condition will kind of be realizable in some sense. If you really have subspace in the data, it makes sense to know the dimension. So it's a good point, actually. Yeah.
If say you ran it with, say, too high of a dimension as your guess, would it still converge and include the true subspace as a subspace in what you learn, or?
So not necessarily. So it's very different than PCA, that you have kind of different components, and sometimes you do something in one dimension and you increase the dimension or reduce it, and the structure is very different. You don't have nested subspaces. So it's very problematic, and that's why it's really hard actually to have an algorithm to find the dimension of the subspace.
All right, let's thank Gilad, and there's a 5-minute break until the next talk.